Dhanasekaran, Assistant Professor, Department of ECE, K.S. Rangasamy College of Technology. In this video, we going to see Ssb-Sc modulation in the course name of Analog Communication. So these are the outlines of Ssb-Sc modulation. Introduction, Ssb-Sc modulation, advantage of Ssb-Sc, disadvantage of SSB, application of SSB, frequency discrimination method and phase discrimination method. So first let you know what is Ssb-Sc modulation. So Ssb-Sc that is single sideband suppressed carrier modulation. So in last video we discussed about double sideband suppressed carrier, that is we use two sidebands for the transmitting signals from one end to another end, whereas in the Ssb-Sc modulation we use only single sideband. The double sideband suppressed carrier modulation signal has two sidebands. Since the two sidebands carry the same information, there is no need to transmit both sidebands. We eliminate one sideband. So why we are going to eliminate the one sideband? Because the power consumption plays the major role in the communication. So in order to reduce the power consumption in the communication system, we have to reduce the signals in terms of reducing the power. So the process of suppressing one sideband along with the carrier and the transmitting single sideband is called a single sideband suppressed carrier system, or simply we can say Ssb-Sc. So it is plotted as shown in the following figure. You can see in this figure here we having a lower sideband, upper sideband and position of the carrier. So lower sideband we can call the Fc minus Fm, and for carrier that is Fc, upper sideband Fc plus Fm. So here carrier and the lower sidebands are suppressed, only the upper sideband will be transmitted. So why we transmit only the upper sidebands means here we can reduce so much power in terms of transmitting the communicating from the one end to other end. So in order to reduce the power, we send only one sideband. So that is Ssb-Sc modulation, that is single sideband suppressed carrier modulation. Here the carrier is suppressed and one sideband is suppressed, only one sideband will be sent. In this, as I said in the above figure, the carrier and the lower sidebands are suppressed, hence the upper sideband is used for transmission. Similarly, we can suppress the carrier and the upper sideband while transmitting the lower sideband. This Ssb-Sc system, which transmits a single sideband, has the higher power, as the power allotted for the both the carrier and the other sidebands utilized in the transmitting this single sideband. So this is the mathematical expression of single sideband suppressed carrier modulation. So you know that modulating signal m of t is equal to am cos 2 by fmt, and the carrier signal c of t is equal to ac cos 2 by fct. So mathematically we can represent the equation of the SS wave as s of t is equal to am ac divided by 2 into cos of 2 by fc plus fm of t. This is for the upper sideband, and for the lower sideband s of t is equal to am ac divided by 2 into cos of 2 by fc minus fm of t for the lower sideband. So for the bandwidth of the Ssb-Sc wave, we know that DSB-Sc modulated wave contains two sideband and its bandwidth is 2 fm. So here in double sideband suppressed carrier we use two sideband, so the bandwidth it is 2 fm, whereas in the single sideband suppressed carrier modulated wave contains only one sideband. You know that its bandwidth is half of the bandwidth of double sideband suppressed carrier modulated wave. So the bandwidth of the Ssb-Sc modulated wave definitely 2 fm divided by 2, that is fm. So therefore the bandwidth of the Ssb-Sc modulated wave is fm, and it is equal to the frequency of the modulating signal. So this is the Ssb-Sc modulation power, the power of the Ssb-Sc wave. So the total power is equal to PUSB, that is equal to PLSB, that is PUSB is power of the upper sideband equal to the power of the lower sideband, that is AM squared AC squared divided by 8R. So from this equation we can calculate the total power the total power equal to the upper sideband power, that is equal to the lower sideband power. If you calculate the lower sideband power, you can get the upper sideband, also you can get the power of the transmission. So these are the advantages of Ssb-Sc modulation. The bandwidth or the spectrum space occupied lesser than the AM and the DSP-Sc waves, because it use only one sideband. So the spectrum space occupied is very less compared to AM and DSP-Sc waves. Transmission of more number of signal is allowed because of the single sideband, and power is saved. We go for the Ssb-Sc mainly for power, and higher power signal can be transmitted through the Ssb-Sc modulation, and lesser amount of noise is present in the Ssb-Sc, and signal fading is very less likely to occur in the Ssb-Sc modulation. And these are the 2 points of disadvantage of Ssb-Sc modulation. The generation of detection of SSC is very complex process, because if you generate a single sideband and detecting a single sideband, sometimes the output filter will not work properly. That's why the detection will be very complex, and the quality of the signal gets affected unless the Ssb-Sc transmitter and receiver have the excellent frequency stability. If the stability will deviate, you will not get the quality in the output signal. And these are the application of Ssb-Sc modulation for the power saving requirement and the low power bandwidth requirement in land, air and maritime mobile communication. We can use Ssb-Sc modulation, and point-to-point communication, radio communication. Ssb-Sc modulation used in the television, telemetry, radar communication, military communication, and amateur radio, etc. These are the possible application of Ssb-Sc modulation, and we can generate Ssb-Sc wave using the following two methods. One is a frequency discrimination method, another one is a phase discrimination method. So this is the diagram for the frequency discrimination method. Here we having the input of M of t and C of t. C of t comes from the local oscillator, that is M of t is a modulating signal, and the C of t equation is AAC cos 2 by FCT. The both two input is given to the product modulator, and the product modulator will give the output of the producting M of t and the C of t, and the output of the product modulator will be the product of the both two signals, and the output of the product modulator will be the DSP-Sc wave, and which is given to the bandpass filter. Bandpass filter will select the specified, that is particularly the which spectrum you want to get the output of, which is going to be selected by the bandpass filter, and the output of the bandpass filter will be the Ssb-Sc, that is the single sideband suppressed carrier wave. So as we discussed in the diagram, the first we will generate the DSP-Sc wave in the help of the product modulator, then we apply to the wave input to the bandpass filter. The bandpass filter produces an output which is Ssb wave. The select of the frequency range, the bandpass filter spectrum is decided by the Ssb wave. The means the bandpass filter can tune to the either upper sideband or lower sideband frequency to get the respective Ssb wave having the upper sideband or the lower sideband. The next method is the phase discrimination method. In this we having a two product modulator and 90-degree phase shifter and local oscillator and summer. Okay, so AM cos 2 waves, that is modulating signal, and the carrier signal will give the both input is given here, and the first input will be 90-degree phase shift given to the product modulator, that is a lag of 90-degree phase shift to one input, and another one as the input is directly given to the product modulator. So both two product modulator will get the carrier from the local oscillator, and the one the carrier is again 90-degree phase lag will be given to the another product modulator. So here two product modulator will give the output. So one is S1 of t, one of the product modulator output is S1 of t, another one is S2 of t. So here the term, that is 90-degree phase shift, will give the lag of 90-degree phase shift output to the product modulator. So product modulator will product the both the input signal, that is modulating signal, and the carrier signal will be given to the summing. So here both added and will get the S1 of t, and the S out of t, S2 of t will be added and will get a S of t. In the phase discrimination method, as we mentioned in the block diagram, so we have two product modulator, the 90-degree phase shifter and the local oscillator. The 90-degree phase shifter produces an output which has the phase lag of 90 degree with respect to the input. Okay, the local oscillator used to generate the carrier signal, and the summer black produce an output which is either sum of the two inputs or the difference of the two input based on the polarity of the inputs. If it is a positive, we'll get the sum. If it is a negative, you'll get the difference of the two inputs. So this is the output of the upper sideband product modulator. So the S1 of t is equal to AM AC cos 2 by FMT cos 2 by FCT. So the finally S1 of t is equal to AM AC divided by 2 into cos of 2 by FCT, sorry 2 by FC plus FM of t plus cos 2 by FC minus FM of t. So the modulating signal AM cos 2 by FM of t and the carrier signal are phase shifted by 90 degree before applying to the input of the lower product modulator. We have the upper product modulator and the lower product modulator. So the lower product modulator produces an output which is the product of these two inputs. The output of the lower product modulator is S2 of t is equal to AM AC divided by 2 cos 2 by FC minus FM of t minus cos 2 by FC plus FM of t. So this is the base discrimination method, that is adding of S1 of t and S2, that is a sum of two inputs equation. So in order to get the Ssb-Sc modulated wave, that is S of t having the lower sideband, so S of t is equal to AM AC divided by 2 cos 2 by FC plus FM of t plus cos 2 by FC minus FM of t plus AC AM divided by 2 cos of 2 by FC minus FM of t minus cos of 2 by FC plus FM of t. Finally you will get S of t is equal to AM AC cos 2 by FC minus FM of t. This is a lower sideband equation. And if you get that is a difference output from the product modulator, that is upper product modulator and the lower product modulator, the S2 of t and the S1 of t, in order to get the Ssb-Sc modulated wave, that is S of t having the upper sideband. So hence by properly choosing the polarity of the inputs, that is a summer black, we will get the Ssb-Sc having a upper sideband or the lower sideband. Okay, so S of t is equal to AM AC divided by 2 cos 2 by FC plus FM of t plus cos 2 by FC minus FM of t minus AM AC divided by 2 cos 2 by FC minus FM of t minus cos 2 by FC plus FM of t. So the final equation of S of t is equal to AM AC cos 2 by FC plus FM of t. So thank you for watching video. Thank you.